So let's review the hyperbolic trig functions. I'm going to focus on hyperbolic sine and hyperbolic cosine because the others, just like with regular trig functions, the other hyperbolics are in the same ratios. So hyperbolic tangent is hyperbolic sine over hyperbolic cosine. So let's just focus on these two for right now, just kind of remind ourselves the definition and the geometric interpretation. So hyperbolic sine, abbreviated SINH, some people pronounce that cinch, can be defined as e to the x minus e to the negative x over 2. And hyperbolic cosine is defined, whoops, I'm doing these as alphas. The reason I'm going to do these as alphas is later on I'm going to, just like you can connect sine and cosine to coordinates on a unit circle, so those are x and y values on a unit circle, I'm going to connect it to points on a hyperbola, and I don't want to confuse the x's that I'm going to be talking about over there, so I did want to do alphas, so I'm going to switch these to alphas. That's the reason I'm using them, just like we might use thetas in trig functions. So here it's the only difference is it's plus. So e to the alpha minus e to the negative alpha over 2 and e to the alpha plus e to the negative alpha over 2. Okay, well, when you realize that that's the definition, then you realize you can use everything you know about exponentials to figure out what these functions are like. Let's analyze them a second. What happens when alpha is really, really big, for example? Well, e to the negative alpha goes to 0. So for very big alpha, that term is disappearing, and these are behaving like e to the alpha over 2. So the long-run behavior for big on the right is that it's like an exponential. On the other end, they have sort of reverse behavior. So let's separate it out here. Let's look at hyperbolic sine first. So let's try and sketch the graph. So if this is alpha and y is hyperbolic sine of alpha, I know that in the very, very big alphas, this is behaving like an exponential over 2, so it's blowing up quite fast. What happens at 0? E to the 0 is 1, e to the negative 0 is 1, so 1 minus 1 is 0. So in the short term, we're going to pass through the origin, but then after a while, we're going to blow up like an exponential. On the negative side, the reverse is happening, right? For very, very small numbers, e to the alpha is heading to 0, and this negative exponential dominates. But there's a minus sign there, so we're going to behave in the long run like a negative exponential, negative e to the negative alpha over 2. So we get this odd function. On the x side, on the positive alpha and negative alpha side, the behavior is flipped. So it's an odd function. Hyperbolic sine is an odd function. Hyperbolic cosine, well, I already said that the long-run behavior for big alphas is the same. Very big alphas, this is headed to 0, so the e to the alpha term is over 2 is dominating there. What happens at 0? Well, because this is a plus, 0 is when this thing reaches its minimum, because that's when this one is 1 and this one is 1 at 0. So you have 1 plus 1 is 2 over 2. So you bottom out. So long run, you're like an exponential. You come and bottom out. And then when you go negative, well, just like with sine, this exponential starts to dominate, but there's a plus sign. So it is a positive exponential. So we're going up on both sides here. So it's an even function. So hyperbolic sine is odd. Hyperbolic cosine is even. One thing that's interesting about that is really one way you can think of these two guys is they are e to the alpha decomposed into its odd and even parts. Because if you add the two together, if you take hyperbolic sine plus hyperbolic cosine, you're going to get that expression, e to the alpha minus e to the negative alpha over 2. And then when you add hyperbolic cosine, you get e to the alpha plus e to the minus alpha over 2. And that half of a e to the negative alpha and that half of an e to the negative alpha cancel because they got opposite signs. And the e to the alpha is reinforced. This is just e to the alpha. So the exponential function can be written as a sum of this odd function and this even function. This is a property of functions. You can actually take any function and write it as an odd part and an even part. And for the exponential, it happens to be those inverse trig functions. What else? Quick application where you might see this. Hyperbolic cosine is the shape you get if you have a chain or rope that's left to hang under its weight under gravity, and it's attached at same height on either end. That sag will be a hyperbolic cosine function. There's some parameters we can stick in here to stretch it, or and depending on the weight of the chain, that could vary a little bit based on some parameters. Or probably the most famous, if you invert that, flip it, so it's a negative hyperbolic cosine, that's the shape they used for the St. Louis arch. That's an inverted hyperbolic cosine function. Okay, I mentioned at the beginning I wanted to use alphas here so I don't mix them up with x's and y's when I compare them to the unit circle. So trig functions, sine and cosine, are the y and x coordinates on a unit circle. We can do something similar here with the hyperbolics. If I draw a hyperbola, the unit hyperbola, so instead of x squared plus y squared equals 1, I'm going to sketch the graph of x squared minus y squared equals 1. And if you recall, you get a hyperbola. Its asymptotes are the line y equal x, y equal negative x. It goes from, I'm only going to, there's a mirror image piece over here, but for our definitions, we only use this piece over here. So I'm going to, it's asymptotic that way to that line y equal x, asymptotic this way to the line y equal negative x. So there's the equation of x squared minus y squared equal 1. So how do we define these guys in relation to this? Well, they are points on it. But where does the alpha come in? There's not an angle. So these would be an angle on the unit circle, that central angle. Here it relates to an area, a signed area. So if I have a point right here, any point on here, and I draw from the origin out to that point, and I shade this region here. So between the hyperbola and that line that connects to the dot and the axis, this area here, if I call that area alpha over 2, then this coordinate is hyperbolic cosine, hyperbolic sine. And the reason I said it's a signed area is, notice hyperbolic sine can take on negative values. So what does it mean to be down here? Well, that area, if it makes an area down here below the x-axis, we call it negative area. So that sort of interpretation of area still holds on the negative side as well. So just like cosine is the x and sine is the y on the unit circle, hyperbolic cosine is the x and hyperbolic sine is the y on this hyperbola. And the alpha relates now to something a little different. This relates to that area as opposed to an angle. While I have that up there, the sort of foundational identity, if hyperbolic cosine is x and hyperbolic sine is y, from the fact that that's our equation, we get our identity looks a lot like our Pythagorean identity for trig functions, right? Sine squared plus cosine squared is 1. Whoops, didn't want to write that. X squared minus y squared equals 1 on a hyperbola. So hyperbolic cosine squared minus hyperbolic sine squared equals 1. So we have a lot of identities for hyperbolic trig functions, but probably the one that's just most obvious is the one that comes right out of that definition there. Before we wrap up, one thing that's really nice, just getting to the calculus of these things, is the derivatives of these. So what would be the derivative of hyperbolic sine with respect to our variable there? Well, that's easy. We know how to do that because we know how to take the derivative of e to the alpha. Its derivative is e to the alpha. Here, by the chain rule, we would pick up a minus. So it would become plus. So the derivative of this would be e to the alpha plus e to the negative alpha over 2, which is hyperbolic cosine. And likewise, if we take the derivative with respect to alpha of hyperbolic cosine, that stays the same, but when we take the derivative of e to the negative alpha, we pick up a negative again, and we're back to hyperbolic sine. Much like the regular trig functions, except for we never pick up a negative, right? The derivative of hyperbolic sine is hyperbolic cosine. Derivative of hyperbolic cosine is hyperbolic sine. No negative, so they just keep going back and forth as you differentiate.